Not least is Dr. John Cooper, who's going to talk about thermoelectric power measurements on some high-temperature superconductors.
Cheer up. So I'd like to present a small piece of work on the thermoelectric power of some high TC superconducting oxides by George Gruner's group at UCLA, and all the samples except for two were made by Barakat Alavi. I have a transparency here about the thermal power, but I think I shouldn't try to explain it at this time in 5 minutes. But one reason why the thermal power is particularly interesting is that in some materials, for example in organic conductors, a large temperature-independent thermal power, a famous minus 60 microvolts per degree K, which you can obtain theoretically for a half-filled Hubbard subband, gives crucial evidence for the importance of Coulomb correlations. So one goal of our work was to see whether we could get systematic behavior of the thermoelectric power, and then to see whether this data fitted the so-called modified Hikes formula, where the log2 represents the entropy of the electrons, and rho is the number of electrons per site. And this formula only holds in the limit of strong on-site Coulomb repulsion, and a bandwidth of the order of the temperature. Actually, it can be about 5 times the temperature. So this shows some experimental results on what we call the pure stuff. This is 2 independent preparations of lanthanum copper oxide. And you can see that the main thing is a temperature-independent large positive thermal power, indications of superconductivity, perhaps from the surface at high temperatures, 80 K, then falling nearly to 0. And then with very small amounts of barium, the thermal power really shoots down. I'll just show one curve. You've seen many this evening of thermal power versus temperature in the superconducting region. This is resistivity versus resistance versus temperature. And you've got a large positive, not very temperature-dependent thermal power in this so-called metallic state. So I'm jumping transparencies. This shows actually, this shows every thermal power sample that we've measured at UCLA. I didn't leave any points off. I added this one so that I could say this. So this is a plot then for 3 different compositions of the room temperature thermoelectric power versus X, where X is determined from the weighed amounts of material. And the point I'm trying to make, this solid line is this theoretical formula where you say that you start off with 1 copper d electron per site, and as you add barium or strontium, you're gradually removing electrons from this 1 copper electron per site. And we think as a first approximation, this line, which doesn't contain any adjustable parameters, shows a reasonable description of our thermal power data up to about x equals 0.1. So in conclusion, the low concentration regime, pure material, thermal power is very large, T independent and positive. This is all above 80 K. Below 80 K there are traces of superconductivity. S is quickly reduced by doping. At room temperature, it seems to us that Sx, thermal power as a function of concentration, both in barium and strontium alloys, can be described by the Hikes formula, which follows from the Hubbard model in the large U limit. That means only 1 electron per site or less, with K T over W of the order of 0.1 or 2. Then for concentrations X bigger than 0.1, or 0.2 in some people's language, S remains hole-like and has opposite T dependence to a metal. Its magnitude is smaller, and it corresponds to a bandwidth about 1/10 that of copper, which is roughly consistent with susceptibility and specific heat data. I'd like, if I could, just to show one more transparency. Oh dear. Oh yeah, here it is. This just shows other work, recent work at UCLA on high-T superconductors. These people are here, so if you're interested in surface impedance in this frequency range, or the effect of impurities, nickel, cerium, or zinc in place of copper, or in other high TC materials, you should talk to them. Thank you.
Okay, we have perhaps